Welcome to the Deep Dive. We're the place where we take a big stack of information, really sift through it, and pull out the important stuff for you. Today, we're diving into something that, honestly, often feels like science fiction, but it's becoming very real: quantum computing. Yeah, we've pulled together some insights from a recent quantum zeitgeist post and also a really good in-depth piece from Live Science. We're going to explore where these amazing machines are right now. So our mission today really is to figure out how many quantum computers are actually out there. What makes them so, fundamentally different from the laptop or phone you're maybe listening on? And what are they actually doing right now versus all the hype about the future? So stick around. You're about to get a solid handle on this cutting-edge tech. Okay, so let's unpack this big question first. How many quantum computers are there in the world today? It sounds simple, but the numbers seem, well, tricky to nail down.
Yeah, it's fascinating, actually. Even just counting them is complex. That quantum zeitgeist post points out a few reasons why. For one, people don't always agree on what exactly counts as a quantum computer. Is it the number of qubits? The architecture?
Okay. Definition issues.
Exactly. Plus, some countries are pretty secretive about their progress, so there's underreporting. And then there's access. Some are stuck in labs.
Right.
While others you can access via the cloud. So that expands the reach, but, makes tracking harder.
Feels like a moving target then.
Uh-huh.
That Zeitgeist article estimated over 100 in 2025. And one commenter, Olivier Ezrati, said he'd personally counted 97. But then someone else, George's L., kind of brought it back to earth, saying, great for research, not there yet for useful commercial applications. So given that, what are these machines actually used for right now?
Yeah, that really gets to the heart of their current utility. Look, the biggest ones have just recently crossed the 1,000 qubit mark. And when we say qubit, that's the quantum version of a classical bit, right? But it can be 0, 1, or kind of both at the same time.
Right, superposition.
Exactly. But most machines today, they have maybe tens or hundreds of qubits. And crucially, they're way more error-prone than classical components. These quantum states are just incredibly sensitive. Any external noise, a tiny temperature shifts, stray electromagnetic fields can mess things up.
So they're delicate.
Very. As William Oliver over at MIT Center for Quantum Engineering told Live Science, what quantum computers are mostly used for today is, and I'm quoting loosely here, basically to learn how to make quantum computers bigger and also to learn how to use quantum computers.
That's a key distinction. So they're tools for their own development, essentially, like learning machines for building better learning machines.
Precisely. Building these larger processors, even if they're noisy, gives us huge insights into how to engineer more reliable ones down the line. And it gives us a platform, a testbed, to develop and try out new quantum algorithms. Plus, it lets researchers test out error correction schemes. That's absolutely vital if this tech is ever going to reach its full potential. The idea there is you spread the quantum information across several physical qubits to create one single, much more stable logical qubit.
Like building a stronger virtual brick from several weaker physical ones.
That's a good analogy, yeah. Companies like Quera, Quantinuum, Google, they've recently shown they can actually create these logical bits pretty reliably. So progress is happening.
Okay, which brings us to the big why. Why are companies, governments pouring billions into something that's still learning how to walk, basically?
Yeah.
What's the fundamental difference that makes it potentially game-changing?
Well, connecting it to the big picture, the secret sauce really is that quantum phenomenon we mentioned, superposition. It lets a quantum system be in multiple states at once until you measure it. For a quantum computer, this means qubits can hold essentially all potential answers to a problem simultaneously.
All at once?
In a manner of speaking, yes. As William Oliver explained it, when you run the algorithm, the wrong answers get suppressed, and the right answers get amplified or enhanced. It's a completely different way of tackling problems compared to classical computers that just chug through possibilities one by one. Norbert Littgenhaus from the Institute for Quantum Computing put it really clearly. He said, it's not just like a fast classical computer. This is a completely different paradigm. Quantum computers can solve some tasks efficiently that classical computers simply cannot do.
Wow. Okay, so that superposition thing isn't just a technical detail. It's everything. It's not just faster. It's a different way of computing, exploring all paths at once, then finding the right one. That really does sound like a paradigm shift. So what does this mean for the future? Where could this actually, revolutionize things? And what's maybe more speculative?
Well, one of the clearest, most promising areas is simulating physical systems, especially in chemistry and material science. These fields are governed by quantum mechanics at their core, so using a quantum machine to model them just makes inherent sense.
Right. Quantum problems need quantum solutions.
Exactly. This could lead to breakthroughs in, everything from designing much better batteries to finding new superconductors, creating more efficient catalysts, even developing new drugs, because you're simulating nature at its most fundamental level.
That sounds incredibly powerful.
It is. Then there's the less positive but very famous application, Shor's algorithm, discovered way back in '94. It showed that a powerful enough quantum computer could theoretically break the encryption that protects, well, a lot of the internet today. Banking, communications, everything.
Yikes. Okay, I've heard about this. Is that still a major worry?
It was, but thankfully agencies like the U.S. National Institute of Standards and Technology, NIST, have been working hard on this. They've already released new post-quantum encryption standards, basically new math problems that even quantum computers shouldn't be able to crack easily. These are being developed and rolled out now to, get ahead of the threat.
Okay, that's definitely reassuring. So NIST is on the case. Does that mean the risk is gone, or is it more about migrating systems over time?
It's definitely about migrating systems. The new standards need to be implemented widely, and that takes time. But the path forward is there. Now, other applications, they're currently a bit more speculative, maybe face bigger hurdles.
Like what?
Well, things like optimization problems, finding the absolute best way to route delivery trucks or manage traffic flow in a city. There's hope quantum could help. But so far, most quantum optimization algorithms don't offer those massive exponential speedups we see elsewhere. The advantage is often smaller. And you have to remember, current quantum hardware is actually much slower in terms of raw operations per second than classical chips. So a small algorithmic advantage can easily get swallowed up by the slow hardware speed.
So it's a trade-off. The theoretical speed-up might not translate in practice yet.
Right. And William Oliver also made another interesting point. He said that as quantum researchers come up with new optimization ideas, the classical computer science folks also keep improving their algorithms. So sometimes that quantum advantage seems to just evaporate as classical methods catch up.
Huh? An arms race, almost.
Sort of. And similar challenges pop up when you talk about using quantum for searching huge databases or for certain types of machine learning. The advantage isn't always clear-cut, or it might be smaller than initially hoped.
So definitely not a magic bullet for every single hard problem out there. But that potential, especially for those simulation problems, seems genuinely huge. All right, you've just taken a deep dive with us into the really complex and fascinating world of quantum computing. We've seen that, look, the technology is still pretty early stage. It's mainly used for research on itself right now. But that unique ability, harnessing things like superposition, it really could unlock answers to problems that are just completely out of reach for us today.
Absolutely. It's still early days, no doubt. And there's so much room for new algorithms, maybe even unexpected breakthroughs that could totally change the game. As Norbert Lütgenhaus suggested, maybe the field should focus more on solving more generic problems first. Then those solutions could branch out into lots of different applications rather than focusing too narrowly right now.
That makes sense. Build the foundational tools first. So here's a thought to leave you with. If quantum computers work by exploring all possibilities simultaneously, suppressing the wrong answers and amplifying the right ones through superposition, what seemingly impossible problems, maybe in your own work or just things you think about in life, might benefit from a completely different way of thinking, a totally different paradigm like that. Something to mull over